Today we're going to be going over, though, what we refer to as the ratio test. And I mentioned at the beginning of class that this is the most important test for Chapter 6, okay? So it's kind of appropriate that we're ending with the ratio test right now anyway. But here's the idea with the ratio test. Let's say that you're given a series A sub n, and I want to determine again if it converges or diverges. Then basically what we are doing is we're going to take a ratio of the next term in the sequence divided by the prior term in the sequence. Now, if you think about this, if you have a sequence of, let's say, I don't know, 1 over n. Let's say that A sub n is 1 over n. Okay, well, that would mean that we have a series, okay? If I were to look at the series, then I would know that that corresponding series, n equals 1 to infinity of 1 over n, is going to equal 1 over 1 plus 1 over 2 plus 1 over 3, and so on, right? All the way out to the nth term, 1 over n. But notice that that's the nth term, so the n plus 1th term is the next term. So I just replace n with n plus 1 to indicate that this right here would be A sub n, while this right here would be A sub n plus 1. So what we're doing in this circumstance in the ratio test is we're creating a ratio by taking the n plus 1th term and dividing by the nth term. Now, two things can happen. Well, a few things can happen, really. But mainly, two things that we're completely interested in are going to happen here. Either that number is going to be less than 1, or the number is going to be greater than 1. Now, let's think about when that would happen. Okay, when is A over B? When is a fraction? When is A over B greater than 1? And when is a fraction here, A over B, less than 1? Okay, so think about that. When is A over B greater than 1?
When greater than the denominator.
Yeah, when the numerator of A is bigger than the denominator of B. But notice that fraction will be less than 1 in the reverse circumstance, when the numerator of A is less than the denominator of B, right? And so now we can think about this as comparing to a geometric series. So basically what we're doing here is we're taking A sub n, n plus 1, the next term in the sequence, divided by the prior term in the sequence. And when we do so, then we are comparing this, or we're kind of comparing this to what we did when we dealt with R, right? If you think about what we meant before as well, when we were looking at a geometric series, okay? Keep in mind that for a geometric series, I knew that the sum from n equals 1 to infinity of A times R to the n, it converges when R is less than 1, but it diverges when R was greater than 1. Now, technically, it converges when R is between -1 and 1. But in general, what we're recognizing here is that if R, the common ratio, is smaller than 1, it converges. And if R, the common ratio, is greater than 1, then it diverges. Well, basically, we're doing the exact same thing here. only now we're looking at it in terms of the next term and the prior term, and saying that if this right here, if this ratio is a fixed number that's less than 1, then that must mean that the next term was smaller than the prior term, so that must mean that it converges. But if you see that a sub n plus 1 over a sub n is greater than 1, then that means the next term is larger than the prior term, which must mean that it diverges. In other words, this would imply this right here implies that a sub n is decreasing. Okay, while this right here, if I get a ratio bigger than 1, that means the next term is larger than the prior term. Okay, and so notice that this implies that a sub n is increasing. And if a sub n is increasing and I'm adding up numerous terms, it's obviously going to diverge. So this is actually a really, really helpful tool to use, because we're basically trying to turn any sequence into a kind of the idea of a geometric sequence. And it's often used, and really the one of the only tests we can use whenever we're dealing with factorials. So I'd just like to start off by doing this problem right here, okay? Now I talked about this idea of absolute convergence, and absolute convergence just means that it converges regardless of whether the values are positive or negative. So one of the first things we talked about in this class was this idea of negative 1 to the n. Does anybody remember what negative 1 to the n does to a sequence?
Alternates?
Alternates what? What do you mean?
It's going to be like -1, 1, -1, 1.
Yeah, all it does is basically change each subsequent term in the series from a negative to a positive. So I'm adding a term, subtracting a term, and adding a term and subtracting a term, and adding a term and subtracting a term. Well, the ratio test allows us to say, since we're taking the absolute value of a sub n plus 1 over a sub n, all that does is it's going to cancel out all of those little negative 1 to the n things. So that's the benefit of actually using the comparison test when we deal with -1 to powers. These are called alternating series. And so in general, that's what we're going to see. So let's just talk about what we did in order to find a sub n plus 1. A sub n plus 1 just meant to go to my sequence a sub n and replace n with n plus 1, n with n plus 1, n with n plus 1, and write it out. That's all we're doing to find a sub n plus 1. To find a sub n, the denominator, well, a sub n is nothing more than just the original sequence. So we just divide by the original sequence. And so what this allows us to do now is it allows us to, first of all, cancel out the -1 to the power, because it's an absolute value. Secondly, it allows us to multiply by the reciprocal. So when I multiply by the reciprocal, take a look at how these terms right here are both 3 to powers, while these terms right here are going to be power functions. So what we're going to be able to do here is try to rewrite this in a little bit of a way, in a certain way. So we've got to do a little bit of algebra. So the first thing to realize is whenever you have powers of n and n plus 1, then let's just go ahead and focus on this one. Okay. Let's just focus on how we would simplify 3 to the n over 3 to the n plus 1. Okay, well, you could do a little algebra and just recognize what's happening. This right here means multiply a bunch of 3's together. This right here means multiply a bunch of 3's together, then multiply by 1 extra 3. Right, so that should be obvious that this is going to simplify to 1/3. Another way to do it is to apply a property of exponents that says 3 to the power of n minus n plus 1. which gives me 3 to the negative 1, or 1/3. So we can see that the purple part right here is just simplifying to 1/3. So now I've got n plus 1 cubed times, or over n cubed, which I can simplify to just n plus 1 over n cubed. So from the ratio test, notice what we're doing. We're taking the limit as n approaches infinity and trying to figure out if it gives me a number bigger than 1 or smaller than 1. Now, if the number is equal to 1, then the ratio test is inconclusive, because all that's telling me is that the numerator and denominator are staying the same as n approaches infinity. So I'm not going to be able to really use the ratio test to test for convergence or divergence. So that's why you're looking for values that are either smaller than 1, meaning it'll converge, or greater than 1, meaning it'll diverge. All right, so now that we've simplified this ratio, basically all we're doing at this point is taking the limit as n approaches infinity of this. But notice that if I'm going to take the limit as n approaches infinity, then I can't really do that, because in this case, that would give me infinity over infinity, which is indeterminate form. Now, some may be thinking, all right, well, I'll just use L'Hopital's rule. But try algebra first. All we would have to do at this point is divide this by n, divide this by n, divide this by n, and notice that it ends up becoming this ratio right here. And when you now take the limit as n approaches infinity, notice that this term right here goes to 0. So all we're left with is 1 over 1 cubed, which is 1/3, and we see that 1/3 is less than 1. And because we got a number that's less than 1 here, that tells me that this series is absolutely convergent. Don't worry about the word absolutely. We didn't really talk about that, okay? Really, all that we care about is that this series is convergent. Absolutely convergent just means that its alternating counterpart will also be convergent, okay? But that's not really necessary. I don't really care about the fact that you know absolutely convergent or not. So really all we're looking at here is the fact that it is convergent. Cool? Everybody cool on that? Why don't we do another one that actually involves, I will just show you the ratio to the root test real quick as well. This is a really simple one that's used oftentimes when you have powers of n. So this one is basically the same general outcome. It's saying if you do something to the sequence and you get a number less than 1, then it converges. If you do something to a sequence and you get a number greater than 1, then it diverges. So it's basically the same outcomes as the ratio test, but the process you use is a little different, okay? What it's saying is just take the nth root of a sequence, and if you take the nth root of a sequence, oftentimes you can find what that particular value is. And you could see that the nth root of a sequence would be helpful if I ever see something like, let's say that I had a sequence a sub n equals, I don't know, let's say 5 plus 3 over n to the power of n. Well, that's kind of a tough sequence to determine whether it converges or diverges, because we get, 5 plus 0. Well, I mean, it's not too hard. We get 5 to the infinity, so it's going to converge, or diverge. But the point of this is, why don't we use the ratio test, the root test rather, because the root test just allows us to say, let's take the limit as n approaches infinity of 5 plus 3 over n to the power of n, okay? And because we see that power of n, we're able to take the nth root of this and cancel out the nth power, which really means that all we're left with is the limit as n approaches infinity of 5 plus 3 over n. And so the limit of this function is, or this sequence is equal to 5. 5 is greater than 1, so that must mean that the series diverges. So that's the benefit of the root test. The root test just allows us to get rid of exponents of n and calculate whether or not it converges or diverges from there. Okay, so this is a really, both of these tests are really beneficial in circumstances that involve powers of n, circumstances that involve factorials, things like that. So I'm going to go ahead and do an example of a factorial as kind of the end of our process here. So let's do okay, let's do an example here. Let's say we want to we've got the sum from n equals 1 to infinity of n factorial squared over 2n factorial. Okay, so remember what factorial means. I want to just reiterate this because this will come up often, very often in the next chapter. So let me just reiterate factorials. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. Okay, but let's look at a few other factorials that involve variables. So what about n factorial? Well, n factorial is n times the integer right below that, which is n minus 1, times the integer right below that, which is n minus 2, all the way down to 3 times 2 times 1. Well, what about n plus 1 factorial? So n plus 1 factorial is going to happen all the time as well because of the ratio test, having to plug in n plus 1 everywhere you see n. So look what that is. That's just n plus 1 times the integer right below it times the integer right below that, and again all the way down to 1. But what you should recognize here about n plus 1 factorial is that n plus 1 factorial has n factorial hidden inside of it. So that must mean that n plus 1 factorial is simply equal to n factorial times an extra n plus 1. So this is going to be a really helpful and important idea here when you're dealing with factorials, because when I start applying the ratio test here, I'm going to be getting these values that are, I'm sorry, we're going to be getting these values that are going to cancel out because of the fact that n factorial is hidden inside of n plus 1 factorial. Okay. All right, well, let's think about what to do then. So when I apply the ratio test, then I am taking the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. All right, well, what that means then is that I'm just going to take the, so again, I'm not looking at the series. All I'm doing is looking at the sequence, and I'm looking at what's happening between the next term and the prior term, right? So in this case right here, I'm just taking the limit as n approaches infinity of the absolute value of, well, let's start off simple and realize that the denominator is just going to be n factorial squared over 2n factorial. What about the numerator? Well, the numerator just means plug in n plus 1 everywhere you see those. So that just means you get n plus 1 factorial squared over 2 times n plus 1 factorial. Now notice that these values right here are never going to be positive as I go from one, or never going to be negative as I move from 1 to infinity. So after this next step, I'm not going to need to write those absolute values anymore. But we're going to do so anyway right now. And so let's just go ahead and start to simplify what this means. Now, I'm not going to by any means just start writing out what n factorial is all the way down to 1. And I'm not going to write n plus 1 factorial all the way down to 1. The point of this is most of these terms are going to start canceling. So let's just think about how to apply this. So this becomes the limit as n approaches infinity. So let's just go ahead and talk about this one for a minute. N plus 1 factorial squared. And also n factorial squared. Well, that just means n plus 1 factorial times another n plus 1 factorial. So let's write that as n plus 1 factorial times another n plus 1 factorial over. Okay. Well, let's think about what 2n plus 1 factorial means. That's just the same as 2n plus 2 factorial. But notice that I'm going to multiply by the reciprocal of this fraction here. I'm going to multiply by 2n factorial over n factorial times another n factorial. So this is where you really have to start thinking about what factorials mean, right? We already talked about what n plus 1 factorial means. It means n plus 1 times 1 integer less times 1 integer less times 1 integer less, and so on. Well, anything that involves n plus 1 is definitely going to involve any factorial that's less than that. So when we rewrite this, we could write this as the limit as n approaches 1, or n approaches infinity, of n plus 1 times n factorial, since that's what n plus 1 factorial means, times another n plus 1 times n factorial, and that takes care of the n plus 1 factorial squared. But before continuing with the rest of this, I'd like to just realize that the denominator on the other side has the n factorial times n factorial. And so this is why the ratio test is good for factorials, because the ratio test will cause all the factorials to cancel. So now let's think about 2n plus 2 factorial and 2n factorial. Obviously, this one right here is bigger. So what does 2n plus 2 factorial mean?
This is 2n plus 2 times 2n plus 1, and then times 2n.
2n plus 2 times 1 less than that, times 1 less than that. But wait a second. From that point on, isn't that just 2n factorial? So from that point on, once you get below 2n plus 1, this is now 2n factorial, because I've got to continue to go all the way down to 1. But look up here. This is also 2n factorial, which means that that whole factorial cancels as well. This is the benefit. This is the benefit of being able to use the ratio test, because it'll when you're dealing with factorials, because it'll cancel all those factorials, leaving you with the limit as n approaches infinity of, well, just n plus 1 times n plus 1 divided by 2n plus 2 times 2n plus 1. Now notice you still get infinity over infinity, but you should be able to simplify this pretty easily. This, if I expand this, this will just become n squared plus 2n plus 1 on top. And on bottom, you get 4n squared plus 6n plus 2. And how do I find the limit as n approaches infinity of that sequence right there?
Since the degree is the same on top and bottom, it's 1/4.
Yeah, you could just compare the degrees and realize that this is automatically going to be 1/4. Okay, so what we've determined here is that the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is equal to 1/4. Now the ratio test is basically the boundary for the ratio test is 1. So the question is this bigger than 1 or less than 1? And what does it mean? Well, because it's less than 1, then that means it behaves like a geometric series where the ratio is 1/4. And if the ratio of a geometric is 1/4, then I know that the series converges. So therefore, a sub n converges. So these are pretty cool. The ratio test is by far my favorite of the tests. And if I could always use the ratio test, I would. And sometimes you can and sometimes you can't. That's the issue. Like, I mean, if you're dealing with terms with nth powers, or if you're dealing with factorials, I mean, you could use the ratio test in a lot more circumstances than you think. Okay, but it's really the only test that we're going to be using when we move to chapter 6, which is on something we refer to as power series. Okay.